Hello friends, in this episode we are continuing with the discussion of thermodynamics. We have already seen the first and second laws and the concepts of internal energy, enthalpy, entropy, etc. and how these are applicable to our two laws. Now we are introducing a new concept or a new property, what we call free energy function, we call it as. It is being introduced because we want to concentrate on the system and to have criteria for spontaneity. That is one of the purpose, and there is other significance also for this function. So we have already seen that for spontaneity you can have one energy factor, maybe internal energy or enthalpy, where decrease in that factor makes a process spontaneous. Similarly, you have entropy factor, and increase in entropy helps a spontaneous process. And we are going to have a combination of these two, and that is what we call free energy. It's a state function in thermodynamics for a system in equilibrium. In a particular state, only we can have a state function, and free energy is also a state function. It has dimensions of energy. It's an energy term. It has dimensions of energy itself. Value is determined by state of the system, not by the path through which that state is attained. It is used to determine, free energy is used to determine how systems will change. That means whether the system will remain in a particular state or it has tendency to go for a more stable state. Or that indicates whether a process can be spontaneous. That is it. Then we can also know the amount of work, the possible amount of work that can be produced during a process. So that is the significance we are going to see, and we are going to see it in detail. Okay, there are two types of free energy functions. Helmholtz free energy function A, and it is often referred to as work function. We will be referring it to as work function. And Gibbs free energy function G, and they are mathematically defined. G is equal to H minus Ts. So we combine enthalpy and entropy there. And A is equal to U minus Ts. There we combine internal energy and entropy. Okay, the change in the function, we can write delta G equals delta H minus delta Ts. And if you consider a constant temperature process, we can simply put it as T delta S. Similarly, delta A is equal to delta U minus delta Ts. And if it is a constant temperature process, it will be T delta S again there. Okay, we have already seen entropy change. We have to consider the system and surroundings. We say entropy of the universe, and delta S universe is equal to the sum of system plus surroundings. And we know the criterion for spontaneity is delta S universe is greater than 0, right? And if it is equal to 0, then there will be equilibrium between system and surroundings. Okay, now we can come to this it in a more detail. Entropy condition itself. Delta S universe is equal to delta S system plus delta S surroundings. It should be like that. And now we can make one substitution. You consider the process is taking place at constant pressure. And at constant pressure, we know the heat absorbed or liberated will be equal to change in enthalpy. Right, delta H is the change in enthalpy for the system. That is the heat. If it is a constant pressure process, that will be the heat exchanged. Then minus delta H will be the heat exchanged by the surroundings, right? If plus sign for the system, minus sign for the surroundings, that's it. Then we can put delta S surroundings as equal to minus delta H system divided by T. The delta H 0 simply signifies we are considering a process taking place in the standard state. That's all. Okay, standard state we will explain later. Right? Why we can apply this here? Because whatever may be the change, whatever may be the amount of heat, as far as the vast surroundings is considered, that is infinitesimal, and hence we can take it as reversible as far as the vast universe, vast surroundings is considered. So we can simply Q reversible by T is our equation. Here the Q reversible for the surroundings can be put as equal to minus delta H. system. So we can substitute that there. So we get delta S universe is equal to delta S system minus delta H system by T. And we know the right hand side of the system of the equation should be equal to delta G system, because it is should be equal to minus delta G system. Why? Delta G system is equal to delta H system minus T delta S. So it is the opposite here. So we can consider T delta S universe is equal to minus Gibbs free energy or minus delta G system. T delta S universe is equal to minus delta G system. That is our significant expression. So this delta G system stands for the total change in entropy multiplied by the temperature at which the process takes place. That is it. So it is another way of expressing the total change in entropy of the universe. So it is standing for the total entropy, and hence we can use it as a criterion for spontaneity. That is it. So this is the same thing. Delta G is equal to delta H minus T delta S. So the opposite of it, that is our T delta S. So it is T delta S is equal to minus delta G. Okay. For spontaneous process, we know delta S universe is greater than 0. Then of course delta G should be equal to less than 0. Delta G system should be equal to less than 0. Sorry, should be less than 0. Should be less than 0. So if there is decrease in free energy of the system, the process can be spontaneous, right? If there is decrease in free energy, what will happen to the total entropy? It will be increasing. That is it. And if the system is in equilibrium, delta G will be equal to 0. And if delta G is greater than 0, that is positive, there is increase in free energy, what does it indicate? The process will be non-spontaneous. That is it. Okay, this is represent a chemical reaction, say reaction between nitrogen and hydrogen. We can see that the reactants have high free energy. This is a curve which shows free energy to the extent of reaction. Free energy to the extent of reaction. So free energy decreases as reaction proceeds. The composition of the reaction mixture changes. Initially we have pure nitrogen and hydrogen. Ammonia is being formed. The composition of the reaction mixture changes. What happens? The free energy of the system changes. It decreases. It attains a minimum value. Further, if the process happens, there is increase in free energy. That means the reaction has attained equilibrium. It will remain as such then under that given set of conditions. If you start from the products, then also that is start from ammonia, then also it will be the same thing happening. That is it. Okay, we have explained it. We can have different spontaneous and non-spontaneous processes, and we have the two factors, the energy as well as entropy factor, that is combined to our free energy factor. Similarly, we can have this Helmholtz free energy or work function, and that is given as delta A equals delta U minus T delta S. If it is a constant volume process, we can consider delta U as the heat exchanged, right, for constant volume process. Now we consider constant volume process. Delta S universe will be equal to delta S system plus delta S surroundings. And delta S surroundings in this case can be taken as minus delta U system by T, because minus delta U system now stands for heat exchanged because it is a constant volume process, right? And for constant volume process, we have this expression, and we can see that T delta S universe in such a case will be equal to minus delta A in constant volume processes. The other one was T delta S universe will be equal to minus delta G in constant pressure processes. That is the difference. Okay, now we can have another significance for this free energy function, and we are going to get that with some mathematical rigor, right? Our expression for free energy is G equals H minus Ts. That we know H is equal to U plus PV. So we can write u plus PV minus Ts. We differentiate this. dG will be equal to du plus PdV plus VdP minus TdS minus SdT. That's our equation number 1. Okay, fine. We are making some simplifications. We take the first law equation, dq equals du plus dw, where du is change in internal energy, dw is the work during the process, work exchanged during the process. And so far as we have considered expansion work, but during processes we can have this type of what you call expansion compression work, as well as other types of work like electrical work or some other type of useful work in a process can happen. That is not of expansion nature, right? Electrical work is a suitable example. That is not of expansion nature, right? In such a case, we have to expand this expression. du is equal to dq plus dw expansion plus dw non-expansion. Okay, and we know expansion work is given as minus pdv. So we can write du is equal to dq minus pdv. That holds good when there is only expansion type of work, but we have to add the other term of the work. The other term of the work in some cases may be 0 or some cases may not be 0. That we do not worry. So we have to put dq minus pdv minus dw non-expansion, right? And also by definition of entropy, ds is equal to dq reversible by t, or dq can be put as equal to tds. Now we can put this equation 2 and 3 into equation 1. We can simplify it. For du, you put that term, pdv cancels. Then for tds, we put dq also cancels. And what will be remaining will be simply dg equals dw non-expansion, work non-expansion plus vdp minus sdt. Now we consider a process is taking place at constant temperature and pressure. Then dp becomes 0, dt becomes 0. That two terms will vanish. And what we get, dg equals dw non-expansion, or minus dg equals minus dw non-expansion, or minus delta g equals w non-expansion. That is it. Delta g equals w non-expansion. What does it indicate? The change in free energy, decrease in free energy. When delta g is negative, there is decrease in free energy. That much amount of non-expansion type of work can be obtained, and we have considered the process to be reversible. And what does it indicate? Delta G, or change in free energy, decrease in free energy, is the maximum possible non-expansion type of work that can be obtained from a system. That is the significance of delta G. In another way, in an electrochemical cell, it is the electrical work that can be obtained by it during the chemical process, the chemical reaction that is happening in the cell, right? And in engines, it will be the non-expansion type of work will be the useful work, just like rotating the wheel to run the car or like that. The network, in Carnot's cycle, we can consider the network obtained from the system as the useful work. In such a case, we can put it as work useful. That will be the useful work there. Right. Maximum useful work under constant temperature and pressure for a process taking place at constant temperature and pressure. So energy that is not extracted as work is exchanged with the surroundings as heat. That is it. If there is a total change in energy represented by delta U or delta H, and there is a difference, and that is exchanged as heat with the surroundings. Similarly, we can have here itself, in this case itself, delta H, suppose that is the total change in energy, total change in enthalpy of a process. Then we obtain a useful amount of work, that is delta G, and there will be T delta S. What does it represent? It represents the amount of heat transferred to the surroundings. That is it. T delta S system will be the amount of heat transferred to the surroundings. That's all. Okay. Similarly, we can show that minus dA is equal to minus dW maximum, or minus delta A is equal to W minus W maximum. and minus delta A is equal to minus delta U plus T delta S. In a reversible process, maximum useful work that can be obtained from a system under constant temperature and constant volume. Constant temperature volume process, the maximum work that can be obtained is what we call, we simply put useful. Here it can be expansion or non-expansion, we need not worry. Here there cannot be expansion type of work. Why? Constant volume process. Then it will be the useful. It is representing the useful type of work other than expansion here. But in the other case, there was expansion. Constant pressure process, there can be expansion. Then what can happen? Delta G will represent the non-expansion type of work. Because constant pressure process, there can be expansion. That is it. Here there is no expansion. Hence, the useful work will be like this one. Okay, that is it. We can consider a process, a chemical process or some other process. So total change in internal energy is given delta U like that, and you get reversible process, you get the maximum work represented by the first bar graph, right? The rest will come out as heat. It is given out to the surroundings, and a part is converted to work. And if it is irreversible, what happens? The total amount will what we represent, that is actually minus delta A, that represent delta A, work part represent. That will not be obtained as work, but only a part will be converted to work. A part will be of the delta A function also will be dissipated as heat. And if no work is done, it is also possible, and a reversible process, no work is performed, then the whole amount of internal energy change will come out as heat in such a case. Okay, this is the same thing. If it is a constant pressure process, the graph will look like that. Right? I have already stated that in an electrochemical cell, the change in internal energy, the change in free energy is equal to the electrical work there. That is the non-expansion work there. And the equation that is true for such cells is delta G equals minus NFE. Right? Why minus NFE? Because work is done by the system. It will be negative. And standard condition, we put it as delta G0 equals minus NF E0. E is the electrochemical potential of the cell. F stands for Faraday, and N is the number of moles of electrons exchanged or transferred during the cell reaction at one of the electrodes. Number of moles of electrons involved in the cell reaction is N. Okay, this is the condition we have already discussed. And if it is a reactants and products, if you are considering a reaction, it will look like that. And what is the delta G for the reaction? Delta G for the reaction is not a constant quantity. Look at the graph. And that will be continuously varying. Because what is delta G for a reaction? We are going to see that delta G for a reaction is the G of the products minus G of reactants. Right? And that depends on temperature, pressure as well as composition. As composition changes, what happens? The G of products as well as G of reactants will change. So delta G will be continuously, delta G of a reaction will be continuously changing during the reaction. And so here we have a graph of G against extent of reaction. The slope of the curve will give you the delta G at that particular point. Right? So delta G, delta RG, we can write delta RG, that is continuously changing during the process of a reaction. Initially it is negative, reaction proceeds, and then it becomes 0 at the bottom of the graph. Then reaction reaches equilibrium, we say. And on the right hand side, delta G is greater than 0. That means it is non-spontaneous. Reaction will occur in opposite direction. That is the signal. Okay. the same graph. Free energy of a reaction, it will be sum of free energy of the products minus sum of free energy of the reactants. And under standard condition also, we take products and reactants in their standard condition and you take the difference. And you can see that this changes with, the first term changes with the reaction, because G of reactants and products depends on the composition. It depends on the composition as well. So it will be continuously changing. And what about the second quantity? It will not change with reaction. It is a standard quantity because we consider initial state as the standard state of the reactants and final state as the standard state of the products. Their difference, that is there. We are not considering the reaction mixture. And delta G0 for the reaction is a standard quantity, it is a constant. While delta G is not a standard quantity, it depends on the condition, depends on the composition as well. That is it. Standard state, we know solid it is pure substance under normal pressure and usually room temperature. That is it. But need not be room temperature. Temperature can vary. Pressure under normal pressure. Gas also, that is it. 1 atmosphere pressure gas is its standard state. Solutions, it will be different. Standard state can be defined in different ways for solution. Right. Okay. Sometimes you can have the delta G0 of the reactants as the G sum of GF of the reactants, GF of the products, that is standard enthalpy formation. We consider the elements from which the substance is formed. Elements, you take the free energy as 0. It is defined like that for convenience. That's all. Okay, now we can consider change in free energy. We can obtain functions for or equations for change in free energy. You take the same expression, G is equal to H minus Ts, that is equal to U plus PV minus Ts, differentiating. You get du plus pdv plus vdp minus tds minus sdt. That's fine. First law, dq is equal to du plus dw, right? And now we consider that only expansion type of work is the process. No non-expansion or other type of work is done during the process. Then what we can write? dw equals minus pdv. So we have made one assumption. There is no non-expansion type of work during the process, right? So we can write du is equal to dq minus pdv. That's the usual form we see. We can use it here. And also ds is equal to dq reversible by t. We can write dq equals tds. And we can combine 2, 3 with 1. Equation number 1. What you get? dg equals vdp minus sdt. That is the expression which will give us change in free energy. And we can integrate that expression to obtain a measurable change in free energy. That is it. And you consider which type of process? A constant pressure process. So change in free energy with temperature, that we can put it as constant pressure vdp vanishes. So dg will be equal to minus sdt. So that can be put as dou g by dou tp, partial derivative we use, because we have fixed some variable. Pressure we have taken as constant. That will be equal to minus s. Similarly, dou g by dou pt will be equal to v. So these two expressions give us the change in free energy. Okay, if it is an isothermal process for an ideal gas, we can do the integration. dg equals vdp, we can write. So dg is equal to RT into dp by p. We can, because v is equal to RT by p. So if we integrate it, we will get delta G is equal to RT log P2 by P1. And if there is expansion, P2 will be less than P1. Pressure will decrease during expansion. And delta G will be negative because work is done by the system. And the reverse is also true. Okay. Without using limit also we can do the integration. Integral of delta dg is equal to RT integral of dp by p. And you can put this expression G equals G0, that is the integration constant, plus RT log P, and G0 we define it as standard state, where we put P equals 1 atmosphere pressure. Then what happens? G becomes equal to G0. That is it. That is the standard state. 1 atmosphere pressure. You take it is a gaseous substance, and it's any substance in its stable state at 1 atmosphere is our standard state. This is solid, it is considered as pure. Okay. Now we can consider a term called partial molal free energy. That is applicable in the case of mixes. A chemical reaction involves different species, and chemistry we deal with the mixtures, and hence this term is important. Any property, partial molal property, may be considered as the contribution per mole of the constituent of the component towards the total free energy. So in a mixture, different components make their own contribution, and contribution per mole of one component is what we call partial molal property, and we have partial molal free energy, and partial molal free energy is what we call chemical potential, right? So we can put it as dou G by dou Ni Tp N1 N2. The number of moles of all other substances are kept constant, and we change the number of mole of particular substance. Then its differential is our chemical potential in differential expression terms. And obtaining this expression, we have rigorous mathematics, we need not know that. In that, we can simply take that definition. Okay, that is it. And we can also show that easily G, total free energy of the system, is equal to N1 mu1 plus N2 mu2 plus etc. Ni mu I plus etc. So mu is the contribution towards the total free energy per mole of a component, and we add all of them together. We can get the total free energy of the system. That is it. And we can have expression for chemical potential, variation of chemical potential, and we write mu is equal to mu0 plus RT log P, where we express it in terms of pressure, how chemical potential changes with the pressure. Mu0 is standard state chemical potential of the substance, but is standard state where its partial pressure is equal to 1 atmosphere. That is it, right? P here stands for the partial pressure of the component. Okay. Similarly, we can have expression in terms of molar concentration as well. Gas also we can use molar concentration, and in solution we can use only molar concentration. Then the expression will look like that. RT log C, that is molar concentration. And what about mu0 there? It is the standard state. There the standard state will be different. It is 1 mole per liter molar concentration, right? So that the second term vanishes and mu becomes equal to mu0. So there the standard state is different. It is 1 mole per liter molar concentration. That is it. Or we can express it in terms of which one also? The mole fraction as well. X mole fraction. And what will be mu0 x in this case when mole fraction is 1? That is the pure substance. That's all. Right? And we know x will be always less than 1 in a mixture. Then mu will be less than mu0 in such a case. That is it. And we have to see that this mu0p, mu0c and mu0x are constants, but they will have slightly different values. Okay, chemical equilibrium we can take into consideration. We have the expression delta G equals delta G0 plus RT log P, mu P equals mu0 plus RT log P, there P stands for partial pressure, and total free energy is equal to N1 mu1 and so on, and delta GR for the reaction it is Gp minus Gr, and what we can do is that we can add all of the products together and subtract it from the reactants, and we can put the mu equation there also, and when you make all the substitution we get delta G equals delta G0 plus RT log Q, where Q is partial pressure of, if our reaction is A moles of A plus B moles of B gives C moles of C plus D moles of D. I have taken it like that here in this expression. We can use other symbols as well. Then Q stands for this pressure coefficient. We can put it in terms of molar concentration also. Then delta G0 will be different in such a case. Because it is standard state, we define in terms of molar concentration, then delta G0 value will be different. So we have to put delta G0P. This is delta G0P. We can have a delta G0Z. There is some difference that we have to understand. Okay. For convenience, we take pressure. Delta G0 plus RT log that coefficient. Okay. And at equilibrium delta G equals 0. So what happens then? Delta G0 is equals minus RT log that coefficient at equilibrium. And that coefficient at equilibrium is our equilibrium constant in terms of partial pressure. So we have delta G0 equals minus RT log Kp. That is our reaction isotherm. And we know delta G0 is a constant, we have already seen, because it is the difference between the free energy of the reactants and products in their standard state. Does not depend on condition. It is a constant. R and T are constants. If you take particular temperature, R is a constant, T at a particular temperature. So if T is a constant, Kp is a constant. If T changes, Kp also changes. That's it. So Kp depends on temperature. That is it. Okay, that much will do for the today's session. We have gone through the term this free energy, and actually there is no physical parameter as free energy. That is our construct. It's only a construct. A function is constructed to deal with systems, and we can get useful information regarding the system. Actually, physical significance is only for internal energy and entropy. All else are our constructs for our convenience. Internal energy has physical, it represents the energy of the particles, sum of the energy of the particles. That is our internal energy. Entropy, how this energy is distributed between the particles. That is actually, we call it as randomness. These two things are important, right? When the distribution becomes more and more random, the energy will become less and less available for work. Entropy increases. That means work is already obtained and we cannot obtain further work from it. That is it. So internal energy and entropy are the important factors. That is it. Okay. Thank you. See you again.